we're going to go ahead and get started. Welcome to the last day of our ZVM training. Just a reminder that this is being recorded and will be uploaded to our website. And all questions should be typed into the chat box or emailed to questions@velocitysoftware.com. Up first is Rich Smersna with Intermediate REXX Programming. Rich has decades and decades and decades of ZVM experience and has been with Velocity for over 16 years. He loves traveling to new places. Go ahead, Rich.
Thank you, Sam, and good morning, everybody. I'm glad you all could join us today. This presentation is going to expand on the first session we had a couple of weeks ago, um, um, building on the topics that we talked about there, including including the sessions that talked about XEdit and CMS pipelines, because they both interface very nicely with REXX, and I'm going to talk about that as well. This is the same reference material slide with the addition of the CMS Pipelines User's Guide and Reference, a very good tool, a very good book to use to understand how pipelines works. First thing we're going to talk about is external functions. Now, an internal function is something that is contained within the REXX program that you're running. There's also built-in functions which are delivered as part of REXX. An external function is in a separate REXX program file that's in your access purview, either on the same disk or on another disk, and they're both called exactly the same way. So the first example here, we have a program called myNameExec, and it is going to return a literal, string literal, Captain Obvious. And in our sample program right under it, example 25 exec, we're going to display a couple of items. We're going to display the time, which is a built-in function. That's what the time function provides for. And then we're going to display the result of the myName function. And in the output on the right-hand side, we run our example 25 exec, and the result of the time function is whatever the current time is in the first display. And the second display, it just provides the output from the myNameExec, which is a function called from the main program. That's, in a nutshell, that's very much how external functions work. The next topic we're going to discuss is diag and diag-RC. The diag variants, which is what these are, can be used to issue some CP diagnose functions from REXX. You can think of a diagnose function as something akin to like a supervisor call in other operating systems. These are usually intended to be used from assembler programs, but REXX has an interface into diag functions. The diag8 function can be used to issue a CP command. So in this parse statement, we are going to run this diag8 function with the text CP query user ID. So this is the CP command that we're going to issue. And as when the response is returned, the parse command will parse out the user ID and the system ID from the response of the command. There's a value here in between them in the middle that we don't care about. So that's what the dot in the parse command does, is it just throws away this, whatever this word is. At the end of the response is a hex 15 value. So we're going to use that as part of the parse command to terminate the command and terminate the sysid variable. This hex 15 is always included as part of the command response when using diag8. The interpret command can be used to execute dynamically built REXX instructions. So this gives us a very powerful capability to build a REXX instruction in a variable and run this interpret command to actually execute it. So the expression is interpreted as REXX code and then executed. And if you need to execute commands based on the contents of the variable, this is a very good way to do that. I use this pretty often in some of the code that I wrote for um, just for that reason. I've built this command, a REXX command, and I need to execute it as an expression. So here's an example. I have this test one exec, and I'm going to interpret this value in this literal value here. So this is itself a REXX instruction. I'm going to multiply 4 by 3, return the value into the C variable, and after the interpret executes and then executes this instruction, I am going to display the value of C. And when I run the command here, I just get the response 12, which is exactly what I expected. Now, of course, I didn't need the interpret instruction to do this. This is just an example of how interpret works. On the right-hand side, we have another program that sets two variables. So a string literal, this is number, and the value 8 is assigned to the B variable. And in my interpret, I'm just going to say C and B, and the result is this is number 8. Exactly as I would expect it. Again, I didn't need the interpret instruction to do this, just showing you an example of how interpret works. Now onto the subject of the program stack. The program stack includes three commands and one function. Using the program stack, I should say, includes three commands and one function: push, queue, pull, and the queued function. Push puts an item onto the program stack, and we're going to talk about how the program stack works next. Queue puts an item onto the bottom of the stack. Pull retrieves an item from the top of the stack, the next item from the top of the stack. And queued returns the number of items on the stack. And in REXX, data is always pulled from the top of the stack. There is no way to get to elements later on in the stack without pulling off items on top. A program stack is a data structure that is used to temporarily store data. It can be used by any program running in a virtual machine, running REXX at a virtual machine. I'm not sure if there's an assembler interface or not, but usually it's used with REXX. A number of languages implement a very similar type structure. A piece of data is either queued onto the stack or pushed onto the stack. When data is on the stack, it could be pulled off the stack. That is to say, if there is nothing on the stack and you do a pull, that just issues a console read. So that allows you to enter data on the console that is then pulled, satisfies the pull and is used by the program. A stack can contain many different data items. It can be a string, it can be a number, it can be a letter, it can be the result, it could be a variable that the value of the variable gets pushed onto the stack. It doesn't matter. The stack can contain pretty much anything. And depending upon how you use it, the stack is either a FIFO stack or a LIFO stack. Now, FIFO stands for first in, first out, which means if you're using the queue command, queue writes items into the stack, sort of like you would write into a file. And so it's one record after another, just like writing into a file. If you pull something off the stack, the first item that was pushed onto the stack is pulled off when you're using queue. LIFO, this is a traditional stack. It stands for last in, first out. So when you push items onto the stack, the last item on the stack is the first item off the stack. And I'm going to show how that push-pull process works. So here's our program stack. This is just the memory area in your virtual machine. Right now, it is empty. If I push item 1 onto the stack, it's going to go into the stack as we would expect. If we now then push item 2 onto the stack, item 1 gets pushed down, and item 2 is now at the top of the stack. Consequently, if we push item 3, items 1 and 2 get pushed down into the stack, and item 3 is now at the top of the stack. And this is how it would look programmatically. So here's the program. Again, my test 1 exec, push, 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 and I'm going to display the number of items on the stack, and the result, as I would expect, is 3, because I pushed 3 items onto the stack, and I get the result. The result of the queued function, as I expect, would be 3. But we get these unknown CPCMS commands after the program terminates. Well, when the program ends, CMS will think anything on the stack is a command, and it will try to execute it. Item 1, item 2, and item 3 are not valid commands, so that's why we just get this unknown command error. Now that gives us some interesting possibilities of being able to push commands onto the stack and have them execute when the program terminates. We can use the drop buff command to delete the program stack. So after my after I display the queued command, the output of the queued function, I should say, I issue drop buff. I get 3, but now no more errors. So this is what I expect. If I had run drop buff before I say queued would give me the result of 0 because the program stack got deleted. Now, when we pull items from the stack, we can just issue this pull command, building on this program over here, and I'm just going to call it from stack. It's just a variable. It doesn't really matter what it is. And what that's going to do is that's going to take the item at the top of the stack and put it into the variable. And then the items below the first item will move up the stack. And if I run my program, I see that there's 3 items still, and it displays item 3. Now, the queued function gives us a way to walk through the stack. And this is a very good way to be able to process all the items in the stack if you need to. So here I'm building on the program again. I'm going to do queued, which is going to run this do block 3 times, pull and say, and I get 3, 2, 1, and the items come off in reverse order as I would expect. Okay, quiz time. Okay. So in the program stack example on our previous slide, why are the values displayed in uppercase? Well, because the pull instruction translates to uppercase. We use parse pull to respect case. This is a topic from the previous REXX session. And the function that tells us how many items on the stack are on the stack is the queued function. Good job, everyone. Okay. We're going to talk a bit about value conversion. This is a set of functions that you can use to change bases, and in some of the work that I do, also displaying hex values. It's very helpful when working with data in varying formats. things like SMF records or monitor data, things of that nature. So here are the functions broken out by base, typically. So there's a binary, character, decimal, and hex functions to convert to different types, to different bases. The Here's some examples. The first example, we are setting a variable c to a hex value. So if you have a literal and you put a x after right outside the quote for the literal, the REXX will attempt to convert that to a hex value, a character, in this case, a single hex character. The say command will convert that character, this is 1 byte, to decimal. So it's going to convert this to whatever its decimal value is. And when we run the program, we get 110. A 6 easy in hex is 110 in decimal. The next example, test 2, we're going to take a 2 byte value this time, fox, 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 dog, and do the same thing. We're going to convert it to decimal. And that comes out to 65,533. Now, both of these examples of C2D assume these are unsigned values. If you want to treat a value as signed, you have to tell the C2D function to how big the field is to include the sign uh, to include the sign, basically. So our fox, 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 dog again, if we tell C2D that it's actually a 2 byte field, that tells REXX that it's a signed value, and it comes up with -3, which is exactly what we would expect. Now, not specifically C2D, but down here in this test 4 program, we can certainly nest functions. So in order to convert this to a binary value, we have to first convert the value to hex, so character to hex, and then we can do hex to binary outside of that. So in order to display this value as binary, we run something like this, and we get the result in binary, 16 bits of binary. Okay. The next set of functions does some additional conversions. We're going to set two values. We're going to set C to 20, and we're going to set X to the result of D to X for C. And what D2X does is it converts a decimal value, in this case 20, to hex. And then when we display the results, we get this on the right-hand side. 20 is 1,4, and that's exactly correct. 20 in decimal is 1,4 in hex. And to expand on that, we're going to do hex to binary of this X value. And the say instruction at the end here displays all three. So 20 in decimal is 1,4 in hex, which is 00010100 in binary. To display some of this in actual running code, here we're taking the subset of a record, a string of characters, basically, and I want the first position for one position in this record. I could have done left one also, that would have worked, but in this case, I'm doing substring, and I'm going to convert it to hex and then convert that to binary. And this is a flag field. So what this allows me to do is this allows me to examine the bits much easier with some character comparisons because it just comes out as a string of characters like this. And the next example, I'm going to take the same, the next byte of the record, byte 2 for 1, and just convert it to decimal. And this is going into an R-type variable. Now, both of these REXX commands are from, I mentioned, running code that does SMF analysis. So here's the flag byte, and here's the record type from the SMF record. Okay, next we're going to move on to date management. REXX provides a very powerful date function. It can return the date in many different formats. It can also convert from one format to another. And help REXX date, the command you could issue on the CMS command line, provides a lot more information about how this function works. So the various date formatting options are listed here. A couple of them are suitable for sorting. So this order date and standard date. It puts the year first, then the month, then the day. That's why these are suitable for sorting. Otherwise, a lot of these functions are used to convert back and forth to and from different formats. So, and here's what the various date formats look like. So I just have this exec that displays the format, the long format name, and then inside the date function is the first letter of the format name. And this works for input format and output format, which we'll talk about soon. So all of these have a short form of the format name. What's interesting here is in the output, we see what they all look like. Normal is if you don't provide an option in the date function, it will return the date in this normal form. And that's exactly what n is. So that's why these values are the same. What's interesting here is this base date, and we talk about the base date shortly. So how do we convert between formats? Well, the full syntax of the date function is right here. So the output format is always first, and then the input date, the input format, the output separator, and the input separator. So we can also convert between separator types, which we will show on our Luno program. So here's our test one exec. I put the line numbers in here so for easier reference. So here on line 2, we're going to set a date D1 to a standard date with dash separators. And in the next line, D2, we're going to create a European date with asterisk separators. Not sure why you would use asterisks, but we certainly have the option to. And in D3, we're just going to create a normal date in normal form. Okay. Now, 5, 6, and 7 do some date conversions. So the output for, let me start here. The input format of D1 is S, which is standard. The output format that we want to display is also S. So, but the only thing we're going to do is change the separators. So the input separator here is a dash. That's what D1 has in it, dashes. And we're just going to change it to slashes. And you can see in the output here, it's the same date, just converted from dashes to slashes. We could have probably done the exact same thing with the translate function. But I just wanted to show how it worked with the date. The next example here on line 6 takes a European format date. That's what D2 is. And we're going to change it to standard format, converting the asterisks to dashes. And that's what this shows us. This is the this date in standard format. And we have this normal date in normal format date in D3, but on line 7, we're going to take the normal format date and convert it to the base date. Now remember, the base date is the number of complete days since January 1st, 0001, assuming the Gregorian calendar is extended back that far. Excuse me. And then the result here is 732,908. So August 21st, 2007 is 732,908 days from the base date. Now, this gives us some very interesting possibilities for calculating time frames between two dates. And that's what we're going to do here. So we have this base date. So we're going to take this normal date in our date function. That's what the N indicates here. This is the input format. And we're going to convert it to a base date. And we're going to do the same thing for, this is actually yesterday, not today, but in normal form and also convert it to a base date. So once we have the two base dates, we can do some math. We can display the difference between D2 and D1, and it gives us 6,909. So that tells us there are 6,909 days between these two dates. Now, converting a difference like this to months, to years, months, and days, that's certainly something that can also be done in a program. Okay. All right. Now we're going to talk about interfacing with system commands. When we're issuing system commands from REXX, we always enclose them in quotes unless part of the command is a variable, which it certainly can be. And when we're issuing system commands like this, CP messages are always displayed on the console. So we're just going to we have a very simple exec that does a CP query rich, and we're going to display the return code because the return code from the CP command is always given back to REXX. When we run this, we get this error, invalid option rich. Typically, this means that the user ID, typically this means that the user ID rich is not defined. But we display the return code, and return code is 3. It is no coincidence that the return code is also the same as the numeric portion of the error message. For CP commands, we can suppress messages and use the set EMSG off command to turn off message displays. And you can display the current setting of EMSG with CP query set. And I think it's right on the first line is the eMessage setting. So on our exec, if we building on this exec, we can set EMSG off, issue our command, display the return code, and the error message is now gone. The problem with this method is that EMSG is still off after the exec ends. So we have to be very careful when if we're going to do something like that. Now, back to diag, the diag variants, there's a diag RC function that provides a return code and a condition code from a diagnose function. And the return code and condition code are dependent on the function itself. So you have to read up on how those diagnose functions work. In this case, there is no need to set EMSG. And for these options, I turned EMSG back on just to be complete about it, right? So here's my program. I didn't tag the name of the program, but in any case, I'm issuing diag RC in this case, the same diagnose code 8, which is issuing a CP command, and CP query rich. And I'm going to display the return code, which is the response from the diag RC command. And then I want to parse the return code value to get the actual return code from diag_rc. And this will make more sense when we look down here in the output. So when we run test one, the response that comes back is what came back from the diag_rc command. The first value is the return code. The second value is a condition code. And after that is the response from CP. So this is the error that came back from CP based on the command. And if I just parse this ret code variable and throw away everything else and display ret code, I see that I also have the value 3, which is the same response I got before. And again, it's the numeric portion of the CP error message. So very much the same thing. No need to set EMSG when using something like this. Now, something that's quite a bit easier is just to use CMS pipelines. CMS pipelines can also be used to issue CP commands. The pipe command itself will eat the error message, but still return the return code, still pass the return code back to you. So very simply, pipe and then the CP command, and we have to have CP here. And we're going to pipe the output into this whole device driver. Whole is just basically the bit bucket. Anything that's output from the CP command or whatever command you issue, or whatever stage you're putting here in the pipeline, it will just go away. It doesn't do anything with it. And then we just display the return code, and we get 3, just like we thought we would. Okay. All right. Next, we're going to talk about interfacing with VM-Link. Now, we've talked about VM-Link in other parts of the classes. VM-Link is a very powerful tool that allows you to link and access a mini disk or access a directory. A mini disk has to be linked first. A directory does not. And so what we're going to do is we're going to access in this case, a mini disk in the example that I'm going to show, get the file mode, and then afterwards, we're just going to release the file mode. The assumption is somewhere in between that, we're going to do something on that mini disk, read a file, whatever, look at the directory, whatever the case is. So the idea here is we're going to access a disk, do something with the files, and then just release it. So here's an example. In this case, we're going to issue the command vmlink rich 195. Now, in this case, rich does exist, and rich has a 195 mini disk. The options that we can provide to vmlink, there's a lot of them, but in this case, for programmatic access to a mini disk that we're going to potentially use, we pass the stem option, give it a stem name. It doesn't have to be RESP. That's just what I typically use. It can be any stem name. And .fm is a tag that says return the file mode. There are a lot of different tags that you can pass to vmlink to get information about what it does. And then all I'm going to do in this case is I'm going to use the stem driver to display the stem contents onto the console. So the RESP stem gets returned from vmlink, and I'm going to display the contents of it on the console. So when I run my test, this is a standard message that gets issued by vmlink, and this is the contents of the stem. It's just one line, And the .fm tag is part of the response, which is very, very important to what we're going to do next. And right after the .fm tag is our file mode. And it's exactly what vmlink returned, R. Next, now I put the response down here for reference. So our resp.1 stem element contains this, okay? And also what I did is I changed the option to include no type. What no type will do is it will eliminate this message that comes out from vmlink that tells vmlink, I don't care about what you have to say. I just want to use the results. Okay. That's what the no type option provides us. Everything else is the same. Then we're going to parse resp1, a variable called resp1, with this template.fm and then fmode. And anything after it, we're going to throw away. There is nothing after it, but just in case, you never know, something might change in the future and output formats change. So we always, good practice is that if we don't need anything after it, we just throw it away. Then I'm going to display the file mode. And the idea here is somewhere in this part of the program, we would do something with a file on the mini disk. I don't have anything to do with any of the files, so I didn't put any code here to do that. But then we're just going to release the file mode. And we run the program. Our say command executes. It says file mode R, which is exactly what we expected based on the output from resp.1 earlier. And if we do a query disk, we'll see the file mode is released because query disk will show us all the accessed file modes. Okay. Next, we're going to talk about how we can interface with CMS pipelines. In this example, we're going to read a file into a pipeline, write it to a stem in array, right? Produce a count of the records. Pipelines enforces that the number of elements in the stem is in the .0 element. That's kind of an unwritten convention. A lot of the code that pipelines, and there's some other tools that also enforce that. So we try to maintain that convention in our code. So the .0 element when we're writing REXX is always the number of elements in the stem. Okay, so here is a test program. We're going to use the read pipe file read symbol, in this case a less than sign, to read this file. So this ZOS trace something 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 on the Q disk, and the file contents are going to go into this stem called SMF records. Yeah, and this is a file full of SMF records. And then I'm just going to display the .0 stem from SMF REXX. And that's going to give us the count. And when I run the program, I get 2,567. And that's exactly how many records are in the file. Okay. Building on that, we're going to refine the pipeline since this is SMF data. I'm going to use this spec stage. Now, spec as was indicated in the pipeline section, spec could be a class all by itself. But in this case, 2.1 references the second byte in the record for 1 byte. That's what this nomenclature is. Byte 2 for 1 byte. I'm going to convert it to decimal. That's what C2D does. And it is no coincidence that this is the same thing that REXX uses. And I'm going to put the result of this conversion in byte 1 of the output from the pipe. So I'm basically throwing away all the records, and all I want is this second byte converted to decimal. In the next line, I am going to, in this pick stage is kind of, it's a filter. So it's going to filter out um, parts of the pipe stream. Word 1 is the first word of the output. There is only going to be one word because I'm filtering out this value. And this equal indicates that I want to look for the value 110. And the 110 is in slashes to delineate it. And then I want to produce a count of the lines and write it to the console. So in this case, I'm not loading up memory with this array. I'm doing the counting right here in pipelines. And the output from the count, I'm writing to the console. I don't care about the file or this byte or this value. I just want to count them, right? So I run my program and I get the count, 1,939. For those of you familiar with SMF 110, 110s, those are CSES records. So there's over 1,900 of them in this file. Okay. Next, we're going to talk about interfacing with XEdit. Now, James touched on this a bit in his XEdit presentation. I'm going to try to expand on it a little. And how we do that with REXX is implemented in what's called an XEdit macro. It's basically a file of REXX code and XEdit commands. That's pretty much all an XEdit macro is. Commands can be passed to the XEdit environment from an XEdit profile. Values can be extracted or obtained from the XEdit environment. Now, this is values that are relevant to the XEdit session, and there's over 100 of them. And we're just going to use one. Now, what's cool about this concept is that you can create panel displays using XEdit macros, not unlike ISPF or CICS, if you're familiar with using those tools. But this is a very powerful tool for writing display panels. Okay. Every time XEdit is entered, a profile is executed. The default is profile XEdit. Now, your XEdit profile can be used to tailor your XEdit environment. James showed this off in his session, how he tailors his environment. This is just another example of what an XEdit profile provides for. These are all XEdit commands. These are not REXX commands. These are not CMS commands. These are all commands that are issued to the editor, to XEdit. To interface with XEdit, a profile can also be used to do some very useful tasks. And we have this program called test2. And in test2, I'm going to XEdit an existing file. Now, for reference, it doesn't have to be an existing file. And actually, in some cases, when I'm writing XEdit panels, I just XEdit some random file name. Hopefully, it doesn't exist. But the idea with that is that's how you write these panels usually, right? So when I'm issuing this xedit command, I'm actually editing a real file, and the profile that I'm going to use is called check test one. And for reference, here is the test one exec that I'm editing. So this is the contents of the test one exec. This is what we used before to count the lines in this file of these 110 records. So it's the exact same file. So the best way to think about um, an edit session and you're programming an edit session is sitting at the terminal and figuring out what commands you're going to issue when and what you're going to do in the session. So the idea here is we're going to issue xedit commands and check the responses from those commands. So here is my xedit profile, check test x check test one xedit, and this slash pick is what I'm going to issue in the editor. This is, again, not a CMS command. It's an xedit command. And what does slash pick do? Slash is short for locate. And then anything after the slash is what you're going to locate. And so in this case, I'm going to locate pick, the word pick, display the return code, and then quit. Quit is very important at the end of an xedit macro because if you don't quit, when your program ends, you're going to be stuck in xedit. So you always want to issue a quit or a file if you're updating a file. So when we run the program, we get this result. And this is all stuff I just said. When we run the program, we get this result. The return code value from line 3 is 2, and then we get this error message from xedit, target not found. Well, it couldn't find pick. Well, if we look back here, well, pick certainly is there, but oops, yep, it's in lowercase. So we have to tell xedit to ignore the case. Well, whoops, first of all, we're going to get rid of the error message. Okay. So we're going to build on the xedit profile to change it to turn off the error message and handle a situation where the term we're looking for isn't found. So if the return code is 2, that we're going to display pick not found. Now this is standard REXX code. Now, so in this xedit profile, we're mixing xedit commands and standard REXX code, and that is certainly allowed. But if the return code is 2, we're going to display pick not found and then quit, and that's exactly what happens when we run this code. The next example expands the code quite a bit. We're going to ignore the case, display the line number on which the target is found, and that's where we use the extract xedit command to get the current line number. So here on line 3, we're going to set the case correctly and do our locate. If the return code is 2, we're going to display pick not found and then quit and then exit the program because we don't want to try to extract the line if pick is not found because we really don't care, frankly. But if the return code is not 2, line 11, we drop to line 11 and we extract slash line. Now, this is one of the many extract options that we have in REXX, and line slash line allows us to get the current line in the editor. Now, if we think about this, when we're doing a locate in in an xedit session, the line pointer moves to the line where the locate happened or where the term was found. So in this case, the pointer is going to move to the line where it found pick. And that is what we're extracting from the editor. So this extract line is going to give us that value. And it returns the value in a stem. And that the first element of the stem is the actual line number. So we can display that as part of the message. So if we run our exec again, it says pick was found on line 4. And if we go back to our reference example, there's pick and it's on line 4. This is just tapping slightly into the power of things you can do with Xedit and Xedit macros. All right, quiz time. Thank you, Sam. What command can be used in an Xedit macro to get information about the Xedit session? And that is the extract command. And what element of a REXX stem is used to contain the number of elements in that stem? And typically it's the 0 element or dot zero. The dot is actually not required, but we typically use dot as a convention. Okay, that is the end of the formal presentation. Thank you very much, Sam, for running the quiz. And yes, you do have homework. So we have 2 homework assignments for you. We're going to, well, I want you to write a REXX function that gets the EMSG setting from the query set, CP query set command, and then reverse the setting, which means if it is on, turn it off. If it is off, turn it on. Display the new value of EMSG. And here's some hints on the bottom. Assignment 2, write a REXX program to put a list of your execs from your A disk into a stem, including the last reference date. And here's a hint on how to get the last reference date. Walk through the stem, calculate how old each exec is in days, and write the file name and the age back to the console. And here's some helpful hints on the bottom about how to do that. Send an email to homework@velocitysoftware.com when you're done, and then send your program homework to the homework user on our system if you're using our system, and that we're using the send file command to do so. This slide is in the PDF deck on the website. I'll leave it up here for a few minutes if you want to take screenshots or use your Polaroid camera to take a picture of it so that you have it for reference. And that is all I have.
All right, thank you, Rich. That was great. We're going to go ahead and take a 10-minute break, so I will set a timer and we'll be back here in 10 minutes.